All right, so with this one, this was one of your homework problems. I wrote a little equation to help with this. All right, so let's draw a little picture here. So we have how many times brighter or dimmer is the sun on Mercury, which we'll call the distance d sub b, which is the distance from Mercury to the sun. The average distance is 0.39 astronomical units. Um, uh, than it is on Earth, where d sub a is the distance that the sun is from Earth, which is called 1 astronomical unit. All right, so let's draw a quick little picture of this. So here's the sun. So here's this is not at all this scale. So this is Mercury. There's Mercury, and then of course there's Venus. It's going to be somewhere over here, and then here's the Earth. All right, so here's the Earth. Now the Earth, we know the Earth is 1 AU. All right, and so that's what we're calling d sub a. All right, and then Mercury is this distance right here, which is 0.39 astronomical units. All right, so the thing is, the way that light works, it's called the inverse square relationship, right? That's why in this equation here, the distances are squared, and so light decreases as the brightness of the light decreases as the square of the distance. So the further away you are, the dimmer something looks. You already probably know that just intuitively, from when you walk up really close to a light, it's much brighter, and when you move away from the light, it's much dimmer. This is the mathematical relationship between the two. All right. So anyhow, so B is going to be this is the distance B. All right. So the brightness B compared to brightness A. All right. So we already know that since Mercury is closer to the sun, it's going to be much brighter. All right, so we already know that it's going to be brighter. All right, so that's that part of the question's already answered. Well, is now answered. And then we take the distance. So it says the distance to A in being the Earth in this case, is 1 squared, right, divided by 0.39 squared. All right, so this is going to give us how much brighter, and it's going to be much brighter on Mercury than it is on the Earth. All right, so remember this is just a comparison of one to the other. All right, so it's going to be, since 1 squared is just 1, it's going to be 1 divided. This is actually a really easy problem once you've done a couple of these. 1 divided by 0.39 squared. All right, and so this is the brightness. So let's see, what is it? Did they tell us? We'll just round to 2 places past the decimal. So on Mercury, compared to the Earth, the sun is 6.57 times brighter. Or you would just put 6.57. All right, 6.57. If the number is less than 1, then that means it's dimmer. If it's greater than 1, then it's brighter. All right. So there's our let's work on the next problem, which is very similar to this one. All right, so here we go. We've got the same very similar situation as the last one. So it says, how many times either brighter or dimmer is the sun on the asteroid Vesta which, by the way, is in the main asteroid belt between Mars and Jupiter, to give you some sense of it. The distance to Vesta is 2.36 astronomical units than it is on Earth, where Earth is 1 astronomical unit. All right, so the way that you do this, of course, is using this equation at the beginning. So the brightness at the brightness at Vesta, which is going to be B here, compared to the brightness at Earth, which is A, is going to equal, well, it's the brightness at Earth squared. So that's the distance to Earth squared, which is, in astronomical units, it's 1 squared, which of course is still 1, divided by 2.36 squared. All right, so this is so, well, right away, if the distance is further than than the Earth, then it's going to be dimmer. All right, so you already know that that's going to be the right answer. All right, so let's see how much dimmer it is. Let's get my calculator. All right, so this was Mercury that we just did. So let's clear that. All right, so it's going to be 1 divided by 2.36. 2.36 squared. All right. All right, so it says let's round it to 2 places past the decimal, so it would be 0.18. All right, so it turns out to be 0.1. It's like 179, so we'll call it 0.18. So on Vesta, there's several ways to look at it, right? So the sun is dimmer by a factor of 0.18. Or another way of saying this would be the sun is 18% dimmer. Sorry. That's not right. The sun is only 18% as bright as it is on Earth, right? So, all right, because you're only getting 18% of the light that Earth receives, because the light spreads out as the square of the distance, right? That's called the inverse square law. All right, so that was I think number 11. Let's do the next one. All right, for this one, we're given the mass of Mercury, 3.3 times 10 to the 23rd kilograms. The radius of Mercury is, the distance from the center of Mercury to the surface, the average distance to the surface. Right, that's what these numbers are. Anyhow, it's 2,439.7 kilometers. Calculate the escape velocity in kilometers per second. All right, round to 1 place past the decimal. All right, so the escape velocity equation looks like this. Just to remind ourselves, the square root of 2 big G, the universal gravitational constant, times the mass. The mass has to be in kilograms, divided by the radius. And so this has got to be in kilograms, and the radius has to be in meters, right? Not kilometers. Okay, so it's given to us in kilometers. The mass is already given to us in the right units. So all we have to do is we have to change R from kilometers to meters, right? So it's 2439.7 kilometers, right? And we know that in 1 kilometer there are 10 to the 3rd meters. That's a 3. Sorry, that doesn't really look like a 3. All right. So this becomes 2439.7 E3 meters. All right. So now we use that number right here. All right, so there we go. And we use the same here. Let me just write it. All right, so it's going to be the square root. I'll put the numbers in. 2 times 6.67 e to the minus 11th, the universal gravitational constant, which never changes, times the mass of Mercury in this case, 3.3 times 10 to the 23rd. So remember, all this is under the radical, under the square root, divided by, 2439.7 times 10 to the third. All right, there we go. So let's do this problem. We could do the whole thing all at once, or we could do it in pieces. That is, you could do what's underneath the radical and then take the square root. All right, so I'm just going to do the whole thing at once. It doesn't really matter how you do it. All right, so here, I'll put this over here. Let's clear that. All right, so it's the square root. All right, so here, let's get it's going to be the square root of 2 times 6.67 times 10 to the minus 11th times 3.3 times 10 to the 23rd, 3.3 times 10 to the 23rd, divided by 2439.7 e to the third. Right, and so then we hit equals, and remember, the escape velocity is going to be in meters per second. All right, no, that's not right. That did something. Yeah, that is not right at all. All right, so sometimes people make mistakes. Let me correct this. All right, I figured it out. This calculator is a little backwards. You have to type the numbers in first. So you type in what's under the square root, and then you hit the square root button. Anyhow, it turns out to be 4,248 point. So that's in meters. To convert it into kilometers, remember that says to turn it into kilometers. Just to divide by 1,000, so I moved the decimal place 3 places, so it becomes 4.2. Right, the answer is 4.2. All right, so let me just write that down. So this turns out to be 4.2 kilometers per second. All right, so it's really 4,200 and something. But all right, let me just show you this real quickly if I have time. All right, so here we go. All right, so let me just show you. Try to do this quickly. So it's 2 times 6.67 times 10 to the minus 11th times 3.3 times 10 to the 23rd divided by 2439.7 times 10 to the third. All right, so that's giving me everything underneath the radical. All right, so that's that. And then with this calculator, it's a little backwards. You gotta, then I'm used to anyway. Then you hit the square root button. All right, so that's what the speed. That's the escape velocity from Mercury. So it's 4,247, right? So you just divide by 1,000. You move the decimal place 3 places to the left. All right, and so that's how I get the 4.2. Right, you don't round it up because it's the next digit is not 5 or greater. So 4.2 kilometers per second. It doesn't really look like a K, does it? Sorry. All right, we'll move on to the next problem.